So for the last week of epidemiology, we're going to go over cohort studies and outbreak studies. And based on everything we've done up to this point, these next two sections should go through pretty easily for you because you've already got a good understanding of the terminology and how we interpret results. And I think you'll appreciate what we've got here. So, you've heard us talk about cohort studies. Some of you all may be presenting cohort studies for your article presentation that you're going to send. And cohort studies essentially start off with some sort of group. In some cases, you know in advance who the comparison group is. In some cases, you may be interested in studying one group and following it through time to see what happens. But ideally, you'll have some sort of comparison group, and they're all healthy and susceptible. You follow them over time. Some of them will have something change, whether it be a health outcome or they die or something like that. So in the case of swimmers, maybe over time they get diarrhea. In this group, they're not swimmers, but they're at the beach maybe, and you follow them for a week and see who got diarrhea, and you can then say, okay, 1 here, 3 out of 5 there, 1 out of 5 here, and you can compare outcomes. Usually you wouldn't just do 10 people. You would do larger study sizes than that. So I think that this should be a pretty easy and straightforward video. Cohort studies are often sometimes called longitudinal studies as well, and they refer to kind of following a group or a body of people, and they're attached to some sort of certain period of time. There are three types actually. We have what are called prospective cohort studies and retrospective cohort studies. And there's a third type called ambispective. Ambispective meaning that you're kind of doing both, retro and prospective. So a prospective cohort study is one where the predictor is measured before the outcome. So you kind of know in advance what you want to do. So in this case, you knew in advance that you wanted to study swimmers and then a comparison group. A retrospective cohort study, the time has already passed, but you can go back in time to know everybody in your study was healthy at a certain point in time. And this is different than the case control design in that you didn't initially seek out who the cases or the controls were. You just went back in time into a general population and then compared what happened to them based on some other exposure. So it's a little difference there. With any of these cohort studies, you could select an equal number of cases, an equal number of controls, or match the number of cases and controls. You can actually, as you're following people through time, you do get cases, and you can also match them up with controls and do an odds ratio doing what's called a nested case control design. We're not going to spend too much time on that. Here's just an example of a case or of a cohort study. We mentioned at the beginning of the class the Framingham Heart Study. It's a kind of a classic example where they've enrolled people essentially at birth. Well, not just, they had adults and then they got the kids of the adults, and they enrolled those kids at birth, and they've been following them for a tremendous amount of period of time. And you can follow them longer than this, but you may have endpoints. And it might be when they have a heart attack or they have heart disease. So you could follow them through time and then see how long it takes before something happens. And in some cases, nothing happens to them. And there are also cases where you lose them and they disappear. So you can have what's called lost to follow-up. One thing about cohort studies that's unique to the case control and the cross-sectional designs is the simple fact that we can also do risk ratios and rate ratios. Cohort designs are in many cases referred to as the gold standards. So as the gold standard, you could imagine it also costs more money. You're having to enroll people, follow them through time, meaning that at some point you're going to have to reconnect with them. In a cross-sectional study, you don't have to follow them through time and keep track of what they said or did or were exposed to at time 0 and then a week or a month or a year later. So Cohort studies are more expensive. But with cohort studies, we can actually measure true risk, the probability of an adverse event happening or an adverse outcome happening in a population. We can calculate the risk ratio. We can also study the rate of disease in a population and compare the rate of disease among the exposed against the rate of disease among the unexposed. So using our 2x2 table, where we have box A, box B, box C, box D, we already know that the odds ratio can be calculated using A times D over B times C. The crude odds ratio is very easy to calculate. A risk ratio is different. It's the probability of disease among the exposed over the probability of disease among the unexposed. So it is A over A plus B over C divided by C plus D. So it's the number of diseases or number of people who get the disease or get the condition of interest out of the total exposed population. So if there was 10 people in the study and 3 got diseased, 3 out of 10, that's 30% is the risk of disease in that group. And then among the unexposed, maybe there was 1 that got sick out of 10. And that'd be 1 out of 10, that's 10%. So it'd be 30% over 10%. The risk of this group over the risk of that group. So you would have a risk ratio of 30% over 10%, which would be 3. The rate ratio has nothing to do with this 2x2 table. The rate ratio is the number of cases over the total person time exposed divided by the number of cases over the person time among the unexposed. That 0 is kind of the E0, the unexposed. We're going to go through a practical example, and with cohort studies, again, we can do all three. We can do odds ratios, risk ratios, and rate ratios. So if I were to tell you to use this information to calculate the odds ratio, you'd first be kind of perplexed and say, well, I can't really do much with an odds ratio because I don't know what my exposure groups are. You could use this information just to tell us what the incidence of disease is. If this was a cohort study, all these people would have been healthy and susceptible to the disease, or all these Pokemon at least. And then I've got my cartoon coronavirus up there. And you could measure the incidence of disease over the person time for the whole group. You could actually get the incidence density rate. You know the incidence, 1, 2, 3, 4, 5, 6. 6 cases out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 6 cases out of 14 participants. That would tell you the, quote, cumulative incidence. The incidence density rate is something different. Incidence density rate would be 1, 2, 3, 4, 5, 6 cases divided by the person time of all of the people in your study, including these 11, we'll call these days, and these 12 days of these 2 unknown people, as well as all the person time of the healthy people. So that's kind of the very beginning of epidemiology, where we introduce you to how do you calculate the incidence density rate in a population. How do you calculate the cumulative incidence? So cumulative incidence is the incidence over the number of participants. Incidence density rate is the number of cases over the total person time of all the participants. So if we were to calculate the odds ratio, though, we would need to know like what's something special about the exposed group. So I've reshuffled these, and we've got kind of the younger, we'll call them the younger Pokemon, versus the older ones. So looking at the younger ones, we'll call them the unexposed to old age. And these Pokemon are older, so we'll call them the ones that are exposed to being older. And we're looking at, we'll say, across a 15-day period of time, how many of them are going to get the coronavirus. So, age, older ones up here which are the bigger ones too, is the exposure. E naught, or the unexposed, is unexposed to the older age, are these. So if we had to calculate the odds ratio, what would we do? So first, we would say, how many diseased among the exposed? 5. How many non-diseased among the exposed? 1, 2, 3, 4. And this one, we don't necessarily know what to do with because we don't have full information. You could call it a no case if you want. If you were writing this up as a report, you could say you excluded the ones that you lost the follow-up. So I'm going to exclude it from the odds ratio calculation. So that's 4. Now among the unexposed, the younger ones, we've got 1 case, and then we've got 2 that we know about that are not diseased. So 1 and 2. And we can calculate the odds ratio by doing 5 times 2 divided by 4 times 1. And that tells us it's 10 over 4. And 10 over 4 gives us a crude odds ratio of 2.5. Easy enough. That's all review. Now we have to calculate the risk ratio. And guess what? We can use the same table to start it off. However, we're not going to do 5 times 2 or 4 times 1. We're going to do the risk of disease among the exposed. This risk over the risk of disease among the unexposed. So, let's start this off. 5 have disease out of 9 total. That's the probability of disease among the exposed. So 5 out of 9 over 1 over 3. So 1 case out of 3 that we know about. And when you do the math on that, our risk ratio is 1.67. And you interpret this almost exactly the same way you would interpret the odds ratios. So you remember before with an odds ratio of 2.5, and these are crude, this is a crude risk ratio, it's not adjusted for anything. We can, instead of saying the odds of disease among the older ones, we say the risk of disease among the older ones is 67% higher than the risk of disease among the younger. So this is just like the odds ratio interpretation. The odds are 1.67 times greater of having coronavirus among the older Pokemon than the younger ones, or 67% higher. It's that difference from 1.0. Make sense? All right, so I'm going to wrap up this video here. In the next video we're going to focus on calculating the rate ratio. And this is different than the risk ratio. They're both called RR in the epidemiological journals. You'll see them called RR sometimes, but you have to look at the methods and read what they said. The interpretation is very similar. The odds of disease are higher among this group than that group. The risk of disease is higher among this group than this group. In this case, the rate ratio, the rate of disease among this group is X% higher than the rate of disease in that group. So we're going to pause there. If you have any questions about these videos, always feel free to reach out to me. Hopefully this is helpful, and we'll continue here in a few minutes.